difference there is because of the angle that we have there. Okay, so essentially you are applying this upwards. Okay, so if you focus on just the y itself, the y is going to be affected by the fg, so it's not going to be total because of the fg. Okay, so what I'm essentially trying to say is this fg is actually pulling away from some of the y that you have there. Okay, and that's the reason why they are not going to be equally the same. You understand?
Yeah.
Hmm. All right, so which force is left there? Normal force, ne?
Mm.
Okay, how do we then calculate the normal force? Suggestions. How do we calculate the normal
I
forces?
think it's isn't the same as gravity.
No, once again, I've mentioned it will only be the same as gravity if there is no force at an angle. Yes, Biggie?
I think to calculate the normal force, we have to say normal force plus Fy is equals to the Fg.
Yes,
Is equals to
100%.
Fg.
Yes, 100%. That is the way to do it. So if you look, one thing we know, I've mentioned this for quite a while. This box is on a surface, like so. So because it is then on a surface, Fg is going down, and then we have these forces going up, like the normal force and the y component. But one thing we know about this box is that it's not going up and down, but it's rather going left and right. Okay, so because it's not going up and down, we can stipulate that the forces here are in equilibrium, and because they're in equilibrium, we can equate them to one another. So then I can take the normal force plus that y component and equate them to fg. Okay, so that's exactly what I'm going to do to find the normal force. So I can say the y component plus the normal force must be equal to Fg. Okay, and then the y component, I found it to be 0.40, and the normal force, I've got no idea. But then gravitational acceleration was found to be 98. Then we do the math, and then I'm just going to hit that in the calculator. We end up with 40.6, 84.6 rather, 84.6 newtons. Any questions on that approach? Yes, Pedro.
Why aren't we using that Fy
Oh, yes.
component
Yes,
equal
yes,
to
yes,
50?
yes. Yes, it's the 50. Where's my? Oh, yeah. It's the 50. It's the 50. And that leaves us with 48.
48.
Yes. So it's for what am I doing? What am I doing? Oh, no, 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 no. This is just a normal force. And this should be 48. Yes. 48 newtons. Yes. So what I can then do now is one of two ways. I can calculate the work done by each individual force that I have there, meaning the friction, the y component, the x component, um, the normal force, and the Fg, and then add up those works. That's one thing I can do. Another thing I can do is I can just calculate the F net. Okay. So which approach can we choose? Which one do you want to use here? Which approach do you guys prefer to use? Or I can just pick any approach.
Yeah, N it's fine. N it's fine.
Any is fine. So I'm going to, in this case, I'll use the fnet. So one thing we know about the fnet is that fnet is going to be fg. Um, fg. Okay, let me not do it like that. Let me just rather visit the diagram entirely. So Looking at the diagram entirely, one thing we know is that all these guys are in equilibrium, all of them. Okay, so essentially they do not perform anything to the F net entirely. But then now when we are considering F net, we're going to then consider friction and the applied force, but not just any applied force, but the X component of the applied force. So I'm going to take the friction and the X component of the applied force. So this will essentially be the X component of the applied force minus friction. Okay. So the X component of the applied force, we got 86.60, like so, minus friction. And friction was given to be 20 newtons. So I'm going to take the 20 newtons as is. And then we do the math. So 86.60 minus the 20 newtons should give us around 66.6 newtons. 66.6 newtons, like so. So now that I've found that, then I can jump straight into the work net. So work net is going to be the net work done, the displacement, and the cosine, and then I can plug in the angle between those two. So which direction is the F net going? Which direction is the F net going? Retabil, Retabile, Retabil, I'm on your case. Okay, nothing from Retabile. Mamello, yes. Which direction is the F net going?
I think it's going to the right
Yes,
because friction comes.
yes, because we got an F net of a positive, and we took the right side as positive, and because of that, the F net is going to the right. Okay, and since we have that object like this, and F net is going to the right, and displacement is like that, then you can clearly see that the angle between the two is 0. Okay, so I'm going to then plug in that. So I've got 66.6, and my delta X is 15 meters. So 15 meters, and then cosine of 0. And then I'm going to get my answer. So multiply by 15, multiplied by, okay, no, I still have the answer, and multiplied by the cosine of 0. And this should give us a weird looking number, 999. Am I the only one who got that?
No, I got the same.
You got
I
the
also
same.
got the same stuff.
Also got the
Okay,
same.
yeah. All right. So that's 999 joules. Weird stuff. Okay. Any questions thus far before we dive into potential energy and kinetic energy? Any questions as far? All right. Okay. So thumbs up. Then I'm going to then continue. Okay. So let's work on more open-end questions. So here we are told that a constant force F is applied to a crate to move it upwards along a frictionless inclined plane. So we've got an inclined plane like so, and then we have a crate, and a constant force of magnitude F is used to pull it along. And you're told that it is frictionless. Frictionless, meaning no friction, like the word literally says, along the frictionless plane, inclined plane, and the mass of the crate is given to be 25 kilos. Is given to be 25 kilograms. When the crate reaches point Q, so this is point Q. Uh, this is given to be point Q. When the crate reaches point Q, its speed is 12 meters per second at this point its speed is that much, or its velocity rather, is 12 meters per second. Okay, and then it becomes 10.8 meters per second when it reaches point R, which is point R is around here. That's where we're going to have point R. Okay. Let me just fix the mouse. I'm having trouble controlling the mouse. Oops. Oh goodness. Okay, yes. Point R. So you then told that at this point, then the velocity is 10.8 meters per second. So this is all we are given. Okay. And you told when it reaches R, you told that R is 3.5 meters further up the incline, meaning that the length of this incline entirely is 3.5 meters up the incline. Okay, and then here we just have angle alpha. This is not given to be anything. Okay, and then they just want us to draw a free body diagram. So this should be easy. Okay, so to draw my free body diagram, I'm obviously going to start with a dot. But which forces am I going to consider in my free body diagram here? Which forces? Yes, Per. Apart from the applied force,
I think FG.
Fg. Okay, which one?
Parallel.
Parallel, and then offense.
Yeah.
Offense. Offense. Okay, no response. All right, so we've Pedro said there's FG parallel. What do we know about FG parallel is that it has to be parallel to the surface. The surface is like this, so it has to be literally next to the surface. So because there is gravity, it will go down this way. And then we should have FG perpendicular. So there's my FG parallel and my FG perpendicular like so. And then going up the incline should be my applied force, which is the constant force F. Okay. And then I should also have a normal force, even though the case is not going to be considered in this case. Normal force, and then going down as well, we have friction. And friction is going down the slope because the object is going up. Remember, friction has to go in the opposite direction of the motion of that object. Okay. Any questions so far? Yes, Per.
Didn't say the box is going the frictionless surface.
Oh, yes, it is going on a frictionless surface. So yeah, I can
Yeah.
let me then. Yeah, I'll then I have to not consider friction. Yes. Yeah. Any other? All right. No other questions. Okay. So then the question that follows says state the work energy theorem. So this is the part that we have to know of, like in detail. What we recall about energy is that we had two kinds of energies. We had potential, and actually it's three kinds of energy. So we had potential energy. And what we know about potential energy is that potential energy is calculated by, we know EP is mgh. No questions asked. Where m is the mass of the object, g is the gravitational acceleration 9.8, and h is the height that that object is at. Then we had kinetic energy. So kinetic energy, EK, is we know kinetic energy is a half mv squared, like so, where same situation, m is the mass and v in this case now is the velocity. Then lastly we had mechanical energy. Mechanical energy, and mechanical energy was basically ep plus ek, would then give us the mechanical energy, emec, like so. Okay, so the work energy theorem says that The work done on an object is equal to the rate of change in the object's kinetic energy, like that. So that is the work energy theorem, and this is a definition that you have to know of as per guideline. Okay. Now, question: is mechanical energy conserved during the motion? Is mechanical energy conserved? I want Ritabile to answer this one. Rita, is mechanical energy conserved?
Sir?
Is mechanical energy conserved in the motion of this object?
I
Not sure.
I
You're not sure.
I I don't think so. I don't know. I'm not sure.
Okay.
It is
Terisan,
conserved, sir. I think there is
Terisan.
no friction.
Okay, when we're talking about conserving mechanical energy, it's not a matter of just friction. Okay, just keep that in mind. We do not just look at friction alone. I'll explain it to you after I've
Okay, sir.
tortured. After I just want to torture Teresano a little bit. Teresano, i- is mechanical energy conserved? Yes, no.
Hey, say
Mm,
why me? Say wait. I
I
think
don't
it
know.
is.
Someone is coming next. You think
I
it
think
is?
yeah.
Okay. All right. So when we're talking about mechanical energy being conserved or not conserved, we do not just look at whether there's friction or no friction. Okay. One thing, let's just talk about conservation entirely. When we're talking about conservation, we're talking about mechanical energy remaining the same. Okay, so let's look at two situations here. There are two types of forces that we can have performing some action here. We have what are called conservative forces, and conservative forces conserve mechanical energy. They do not change mechanical energy. Then we have non-conservative forces. Non-conservative forces. Okay, conservative forces, remember, these are the ones that change mechanical energy. If we look at mechanical energy quite close, we have this whole mgh thing going on and so forth. Okay, we can see that some of the forces that conserve mechanical energy or that keep mechanical energy the same are forces that should not necessarily affect things like the velocity and so on directly. Okay, so when you look at conservative forces, we're saying that these do not change mechanical energy. They do not affect EMEC. Okay. And examples of these forces that you can have are forces like the normal force and forces like your gravitational acceleration. Okay. And then when we look at non conservative, we're talking about those that change uh, the EMEC. They're going to cause this mechanical energy to change. This is, I'm sure you can see a good example is an applied force. If I apply a force to an object, it will affect velocity. And because it affects velocity, it will affect mechanical energy. So that is one of the forces that we have to then look at. That is applied force. Friction is also one of them. And also tension is also another example of a non-conservative force. So with this in mind, I'm going to torture Teresano once again. Is the system, is mechanical energy conserved in this system? Teresa. Terry, is mechanical energy conserved?
Yes, it is conserved.
Okay,
I think so.
let's try again. Is mechanical
It's
energy conserved?
it's
Okay,
not.
look here. We said if it is conserved, then the only forces you would have are either those ones that you have on the left. If it is
Mm,
not conserved, it's those that you have on the right. Now, here in this situation, we have an applied force, and because there's an applied force, it is not conserved. Do you see that?
okay.
Exactly. As long as you have those forces like the applied force, friction, and tension, it is immediately not conserved because our applied force is going to add or manipulate the velocity. Okay, and because of that, that's a different. Then we're going to have that mechanical energy not being conserved. Okay, are you fine with that? All right. So now that we got that out of the way, um, give a reason why the normal force has no work on the crate. I'm going to take this one to Petro. Why is the normal force having no work on the object? Let me go back to the diagram while you think. Why is the normal force having no work on the object? Where is the normal force? Why is it having no work on the object?
I think it's because it's on the inclined plane and it's there's no friction. There's no friction. That's why it's not. Yeah,
Not the
like
answer I'm looking for. No. Begimpilo. Why is the normal force having no work on the object?
You say, can I think of it first?
No.
How can I answer without thinking first?
Improvise. Yes, Pedro.
I think it's because there's non-consecutive forces. That's why
Con-
it's not.
conservative.
Yes, and the normal
Uh,
force is consecutive. That's why it doesn't
not
work.
quite. Not quite. Um, remember when we're looking. Okay, Ritabile wants to try. Yes, Rita.
So can you please repeat your question?
Why? Give a reason why the normal force has no work on the crate.
Is it because it is perpendicular?
It is perpendicular. Close, but not the one.
Ah,
Not the one. Yes, it is perpendicular. Um, this is that's if you use the perpendicular reasoning, then you would have to explain it mathematically. So here we have cos perpendicular meaning 90 degrees. Someone raised their hand while I'm about to answer the question. Hi, Marapeto. Yeah.
No, I think it's because the applied force is not on an angle. It's like it's on a straight line. I think so.
not, not quite. Actually, the perpendicular is what actually answers the whole question. Remember, cosine of 90 gives us 0. And because cosine of 90 gives us 0, then the whole work expression just becomes 0. And therefore, the work done is just 0. I get it. And then you've also mentioned the whole situation about conservative. This is us just saying, look, the reason why it's not performing any work done on an object is because it does not affect the movement of the object. This guy is going up there, and in fact, if you look at it, he actually cancels out with this guy. So ultimately, he's doing nothing. Do you see that? Are we cool with that so far? All right. So moving on. Now the devil has arrived. Now they're asking, use energy principles. This one always comes a lot, guys. Use energy principles to calculate the magnitude of the force F, which is that applied force that we have. What do they mean by energy principles? Energy principles, there are two equations that we regard as energy principles. Okay, so when we're looking at energy principles, you can either use either the equation network done on an object is equal to the rate of change in kinetic energy, EK. This is one of the equations you can use. Another equation that we regard as a work energy principle is work done by the non-conservatives is equal to mechanical energy, or work done by the non-conservative work done by the non-conservatives is going to be delta EK plus delta EP. When we're talking about work energy principles, it's any of these two equations, and you have to really judge by the scenario which equation would work well here, depending on what you're given. Okay, so you really have to have that judgment to say, look, this equation works best and this one does not. Okay, so out of this scenario, which equation can we use? The W net or the WNC? Which one? Which one can we use? Tirisan. Ter, I'm back. Hey Ter, the devil is knocking at your door. Which equation do we use here? You thought or you can hide. Which equation do we use here? Tirisan, I'm here, pal. I guess not. Retabil, which one can we use here? Which equation would suffice to use? Should we use the non-conservative or should we use the W net, judging by this scenario?
So
Yes,
I think, Retably thinks that we should use the yo. I maybe the WNC one.
the
No,
WNC one.
I don't know. The
You don't know
WorkNet.
the work net.
I think.
Okay. Petro.
The first one, because the second one, I think we don't have the height of the.
Yes, one hundred
So
percent. We
we
do
have to
not
use
have
the
the
first
height.
one.
Perfect,
Yes.
perfect, perfect. Beautiful, beautiful. And even if you try to find the height, actually you can't even find the height as well because you're not provided the angle of the incline. So the one that would suffice is the one for the non-conservative that says, I mean the one that says W net. Do you see that? So uh moving back to it. So if you look at this equation, the one for the non-conservative just needs we know that delta ek is has the mass and velocity, and we have these masses and velocities. We actually have velocity at q and the velocity at r. So we have that. Even the mass of the object, we have this. So this is just pizza Monday. Okay, but now the one with the non-conservative, the potential energy part is the one that's going to mess you up because you're not provided the height. So that becomes a problem to calculate. So the equation that would suffice here in this case would be the one for the W net. So what we know, let's work on the W net part first. So here, just keep in mind, they're asking you to calculate the magnitude of F. Okay, they want you to calculate F. So I'm going to start off by making just the substitutions for this. So what we know about the WNet, we know that the network done is a result of the work done by this applied force minus, or rather plus, because it's a net, plus the work done by the friction. We do not regard the FG perpendicular and the this. So actually not the friction, the parallel. So we're just looking at only these two, the FG, the work done by the FG parallel and the applied force only. So the net work is just the work done by the applied force plus the work done by gravity parallel, and this is equal to the rate of change in kinetic energy. This is actually a very interesting question. So once we've got that in mind, then we're going to have to do a whole F change in x cos theta for each of these, and this side we have to do the half mv squared thing. So let's expand these expressions. For the F, we know that F delta x cos theta is the equation to go to for this. Then for the parallel, we know that we're going to say plus FG parallel because that's the word, we're working on this force. FG parallel delta x cos theta. And this is equal to a half. And remember, this says delta, guys. Because it says delta, you're going to have to say final minus initial. So we're saying the final kinetic energy minus the initial kinetic energy. So I'm going to have to say half mv f squared minus a half mvi squared. Any questions on the expression so far? Any questions on the expression so far before I continue with the substitutions? All right, I'll take that as a yeah, as a no question. So then I'm going to start by making then the substitutions. So I do not know what f is. Actually, this will help me calculate the f. But then the delta x, the displacement, we told the displacement of the incline to be 3.5 meters. So that's where my 3,5 comes into play. Then I've got a cosine theta. Now this theta, remember this is work. So the angle between the f and the theta is actually 0. Okay, plus, and then FG parallel. So remember FG parallel, we may have to calculate this one on the side. Okay, so to calculate FG parallel, we remember we have to use the sign. So FG parallel is equal to mg sine theta. Let me just plug this directly into the equation. So because it is mg sine theta, I'm just going to put in a giant bracket for that. So we know the mass is it 25? Yes, 25 kilograms, the mass of that object, and the displacement was 3.5. Okay, and then sine theta, and theta in this case, this theta that we're talking about is then the 30 degrees. So this was supposed to be for the incline. Oh, I never gave you the incline as 30 degrees. Okay, then this substitution that we just made is not for this whole thing. It's just for the FG parallel. Then I still need this displacement. So for that displacement, I still have the 3,5, and then I still have cos. And then this time parallel is going down the slope, but displacement is around there. So the angle really between them is 180 degrees. So I'm going to put in cosine of 180. Any questions on my substitution so far? Yes, Rita.
So can I ask, why did you use 3,5 instead of
Uh,
9,8?
3,5. You mean for the G? Yes,
Yes.
yes, yes, yes. That's an error. Yes, that's supposed to be 9,8, not 3,5. I put in a displacement there. This should be 9,8. Yes. Any other questions? Offense.
I wanted to ask the same question, so it's fine.
All right. All right. Any others? All right. I'm guessing we're fine. Then we're gonna work on the right hand side then. So for the right hand side, we've got this whole blah blah stuff. So half. So now let's really look at the whole projection and the whole motion of this object. So he started off at R. Or at Q, yes. At Q, its velocity was 12 meters per second, and it traveled to, or it actually deaccelerated to 10,8. So it started at 12 and ended up at 10,8. So my final, actually the mass is the same, so it's still 12. No, not 12, 25 kilos for the mass, and then the final velocity is its velocity at r, because it was traveling towards r, and the velocity there was 10,8 meters per second. So I'm going to have then 10,8 meters per second there, and we have a square minus a half, and we still have 25, and then initial velocity, this was the velocity at q, which was 12 meters per second. So I'm going to have my 12 there. So out of this whole thing, you can then realize that the only unknown that stays is the f that we are really looking for. Okay. So I'm going to, yo, Jesus. Hi, this is a long solve. Hi, no. Whew. Hey, okay. I'm going to make use of the calculator. So, or you guys can also go ahead and try calculating it now, and then you can just shout out the answer once you have it. Okay. Go ahead and calculate it. Yes, Pet.
I think it's 24,79.
24.79.
Yeah.
Okay, let me just double check that. Um,
I also got the same.
you got the same. I have trust issues with school kids, so you guys will have to give me a minute. You said it was how much?
24,79.
For the value of f.
Yes.
24.7. Okay, yeah, I got the same. Okay, so then f is 24.79 newtons. Beautiful. Any questions on that solve? Any questions on that solve? Petro? All right. So no questions on that one. Then the last one for this work, energy and power, I have this very interesting one. We are given a roller coaster, probably somewhere around Sun City or wherever they have roller coasters. Um, the rail starts from A and then it gets to B and then up until C. Okay. So a roller coaster consisting of mass 200 kilograms. So you have a roller coaster. Excuse my bad artistic skills. So you told the mass of this roller coaster is 200 kilograms of this roller coaster. And at A, so the mass of the roller coaster is 200 kilograms with an engine that travels from A, B to C. And it is on a rough surface. So meaning the whole rail is a rough surface. At A, which is 10 meters above the ground. So here, A is 10 meters above the ground. A is 10 meters above the ground. The speed of the roller coaster is 4 meters per second. That is the velocity at A. At B, which is H above the ground, this is unknown. It is H meters above the ground. Um, the speed is 2 meters per second. So when it gets to B, the velocity is 2 meters per second. Um, during the motion from A to B, it consumes 3.40 times 10 to the third joules of energy. So meaning through its entire motion from here to there, it consumes let me just get rid of that 3.40 times 10 to the third joules of energy to go from A to B. To overcome that whole friction and all that. Okay. You're told to ignore rotational friction of the wheels, so you don't have to worry about the friction between the axle and the wheels. Use work energy principles to calculate H. Oh, and C is 2 meters above the ground. Use work energy principles to calculate that C. Okay. So you guys dot down that question. So here you asked to use energy principles uh, to calculate H. Okay, so I'm just gonna zoom this out and then we're gonna take a break while you guys work on this question. So you can take a screenshot or whatever, and then in about 10 minutes we're gonna then come back. You're gonna use the same link to join the very same meeting, and then we're gonna compare the answers. Okay, you guys fine? You can take a snapshot. Okay, give me a thumbs up when you're done. When you've dotted out the when you have dotted down the question. Thumbs up. Durasa no. Okay. Okay. Petro.
That's fine. I'm fine.
You got it. And Tato, Ivan, Kante, he. Okay, Tato. Yes, Biggie. Yes, Biggie, your hand is up. Biggie. Okay, no. Tirisano, you've got the question written. Tirisan,
No, so I'm still busy with it.
how? Take a screenshot, Pela. Okay, yeah, you can jot down the question. We're still in the very same meeting. I'm not gonna close it or anything. I'm just gonna mute it and then you guys can work on that question. And then in about 10 minutes, meaning at 9:35, I'll come back and we'll then compare answers for that question. All right, guys, I'll see you in 10 minutes. All right, I'm back, everyone. Can you guys hear me?
Yes,
Or you
yes.
guys, or you can hear me? Are the others even there? You'll find one of
Yes.
them passed out and slept. Okay, so let me start with offense. What answer did you get for the height?
I got 2.35. I'm not sure.
Okay, Petro, what did you get for the height?
Hey, I don't wanna know. Hey, hi, this one, you. Okay,
No, I want to know.
I, I think, but I'm not sure about it. It's 12, comma, let me check. 12,35. You see, it's
Yowza.
12,35.
Re thabile. Re thabile.
So I got 10.61.
Okay, and then Tatu. This guy's been quiet.
Ish. I'm not sure. I got 1,53.
How, guys? Where are you getting these numbers? Eh, Mamelo. 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 Nothing. And
I'm
okay.
struggling with the microphone. I got 2,65.
Ivatru. Terry, help us.
I say it's not make sure. Mina, I got 5.92.
Okay. Okay. All right, guys. I want you to note this. Ne? Whenever you have a curve somewhere, as long as there's a curve in J, like this thing, it's a curve. Use NC. Okay, so the one that would suffice to use is the work done by the non-conservative is equal to mechanical energy. This is the formula that I believe you guys have at least tried to use and then probably messed up on the substitution, maybe. So this is EP. Yes. This thing stopped moving. Okay, there we go. So let's see what we are given. First things first, we were given the work done to overcome friction. Work done to overcome friction. Friction is a non-conservative. Because of that, that is actually the value of the NC. So it's 3,40 times 10 to the third. So that's my value of the non-conservative times 10 to the third. Reason being, remember, work is given in joules, and really that's the only thing that is provided in joules. So that is the what I'm going to then use. Then for the kinetic energy and the whole thing, I'm just going to expand this formula. So I've got the whole delta thing. So this is essentially just going to be this thing is misbehaving. Yes, half. Jesus, um, it's off. Okay, so half mv f squared minus a half mvi squared. That's delta ek plus delta ep, which is going to be mg. Remember, whenever you see a delta, this is always final minus initial. Whenever you see this, it's final minus initial. So this is going to be mgh f, the final height, minus mgh I, which is the initial height. One thing we do know is that it is traveling from A to B. And because that is the case, then I'm going to have that as an initial height and the final height being the H. So let's make the substitutions. So here I'm going to have a half, and then the mass is 200 kilograms. That is simple. So I have a 200 there. And then the final velocity, which is actually the velocity here, that is 2. Then I have the square, then a half, mass is still 200, and then initial velocity, which was the velocity at A, which is 4 meters per second. So I've got a 4 there, and we still have the square. Yo, worst handwriting. Yo, Jesus. Square plus. Then here we have the mass of still 200. So I'm going to plug in the 200. Why is this thing dying on me? Yes, 200. Gravitational acceleration 9,8. And then I have the final height. Final height is this one. So that's the height that it was finally, minus the initial height, which was the height at A, because remember it's moving from A to B. So then here I'm going to have the very same 200 times 9,8, and then initial height, which was the height at A, which is 10. 10. Does anyone have a similar substitution to that? Anyone?
I wrote exactly that. Exactly that.
Then what did you do wrong or right?
No, like I just said, no, I got the same like 12,35. You like continue.
12,35.
Yeah.
Okay, let's find out. Okay, actually this should be a negative because we're talking about friction. This should be a negative. Let me do this. Equal to, because it's done by the non-conservative, and the non-conservative there is friction, and friction is negative. So here we should be having a negative. So let me just do quick solve with the calculator. So negative 3.40 times 10 to the third is equal to, let me just simplify this. So if we simplify this, how much do we get? If we simplify the kinetic energy, how much do we get? Just the kinetic energy. Anyone? Oh, guys, you're in got calculators or anyone? What is the kinetic energy equal to? What does the kinetic energy give us? Yes. Ratabil.
So is it negative 1,200?
Yes, we get a negative 1,200. So negative 1,200. Okay, and um, then we have a plus. So plus this. And what do we get for that one? What do we get for the potential energy? And of course we have to include the H. So what do we get for that one? Yes, Pedro.
It's 1,960 H minus
Uh-huh.
10,000 and
Minus
19600.
19600.
Yeah.
Hey,
10,000 minus.
let me double
Yeah.
check that. Okay. 196,000. Okay. And then this side we still have this 3,40 times 10 to the third. Then we just need to then isolate the H. So now it actually looks clean. I can work with this. So let's get the final answer. 10 to the third. Yes, Pedro.
Hey, you made a mistake. There's only two zeros, not
Where?
three. It's not like here at the front. Like it's
The
not
oh yes, yes,
100,000.
yes.
Yeah.
I have an extra zero for that. Yes. All right. What is the value of H? Yes.
8,88 meter.
Yes, 8,88 meters. That's the answer. 8,
But why didn't you tell us that that's negative?
I don't have to tell you. You know it's the
Yeah, but
non-conservative, and non-conservatives are
you're
negative.
including it now. You're including it now. Like you were supposed to be. Yeah, serious.
Baba.
Like that's why we got wrong there. Like that's the mistake. Only that's negative. That's negative.
But case in point though, it is a non-conservative, and the non-conservative you had there was friction. You had to let it come to mind that it has to be a negative. All right. But nonetheless, that is then the final answer that we have for that question. So shall we then move to electrostatics? Thumbs up if you guys have any queries. We can move to the next one. All right. So let's go into electrostatics. So electrostatics is the whole study with charges and the waters and yada yadas. Just get to the page. Oh yes, there we are. Yes. So quick revision of the most basic stuff. So before we look into Coulomb's law, let's just discuss the atom. The atom. The atom, you guys should know this. So the atom is made up of three things, right? What are the three things that make up an atom? Offense. Offense. What are the three things making up an atom? Before we understand what charges are and everything, what are the three things that make up an atom? Okay, Tado.
I don't know. I think
Ah,
electron,
So
proton,
you
and
said
I don't know the other one.
good. Yes, we're going to have an electron surrounding the neutron, right? The nucleus. So we have an electron, E minus, and then in the middle we have the nucleus, and the nucleus is made up of the proton and the neutron. Good. So with this in mind, we can then look at it and really understand what charges are all about and how charges are developed. So here, when we're talking about the atom, keep in mind that one proton will have a charge of 1.6 times 10 to the negative 19th coulombs. One single proton will have that. Okay. And we know that protons are positively charged and electrons are negatively charged. So one electron is going to bear the same amount but negative. So an electron is going to bear negative 1,6 times 10 to the negative 19th coulombs, like so. So this is the charge of those individual quantifiers that make up the atom. Okay. So once we have this in mind, we then have to come to the understanding that when an entire object is positively charged, it's because it has more protons than electrons. And then if it is negatively charged, it just means that it has more electrons, like so. That's actually an E. Okay. Then we have to look at the laws of thermodynamics. There are laws to this whole attraction and repulsion. And I'm about to torture Teresa to actually tell us what are the laws of attraction and repulsion. Teresa, Terry, I'm here. Teresa, yes, Terry. What are the law? What do the laws say?
Samina, I don't know.
Ah, yes. Offense.
Law of attraction. Unlike charges attract and then unlike charges repel. Is that how
Wait,
we answer?
wait. What?
Unlike
Unlike.
charges,
Uh huh.
unlike charges attract and then like charges repel.
Unlike charges attract and like charges repel. The first time you said unlike attract and unlike repels.
No.
Anywho,
Okay, sorry.
okay. So what we the case in point is, suppose we have arbitrary charges Q1 and Q2. Um, if Q1 is say maybe positive and Q2 is negatively charged, then the case that we'll have is that they're going to attract like that. They're going to then move towards one another. Then, if you had unlike charges, suppose you had one which is positive and one which is positive as well, then they are going to repel. They're going to go that way and that way. Same thing would happen if they were negative and negative. As long as they are unlike, then you're going to have that scenario happening. So, this whole attraction and repulsion, it is a force. And because it is a force, we're able to calculate it. So, the way in which we calculate it, there is a certain formula that was developed by a scientist named Coulomb. And then this is where he came up with what is known as Coulomb's law, which is used to calculate the electrostatic force, which is either that attraction or repulsion. So that electrostatic force is calculated by his Coulomb's law, which is then F is K, Q1, Q2 over R squared, where Q1 and Q2 are the charges of those two. And then K is known as the Coulomb's constant, which is equal to 9 by 9. No, not 9 by 9, but rather 9 by 10 to the ninth. Okay? Um, this is the way you have to know the Coulomb's constant to be. Even though there are many ways to calculate even the Coulomb's constant, I recently learned that Coulomb's constant is actually equal to 1 over 4 pi epsilon, which is quite interesting. Epsilon, very, very interesting. Don't worry, let me not scare you. Uh, so keep those in mind. Then um, we have to know our units, guys. We have to know our units. One thing, force has to be in newtons. Um, charges have to be in coulombs. And then the distance between those two charges always has to be in meters. Okay. And then let's talk about conversion. You have to know the ways to convert between those quantifiers. So starting off with those charges, one thing you have to know is that 1 microcoulomb, 1 microcoulomb is where we're going to use the 1 times 10 to the negative 6 coulomb. So 1 microcoulomb is 1 by 10 to the negative 6 coulombs. And 1 microcoulomb is 1 by 10 to the negative 3 coulombs. And 1 nanocoulomb is 1 by 10 to the negative ninth coulombs. Those are the conversions you have to know in terms of just the electrostatic, no, not the electrostatic forces, but rather the charges. There's a hand up. Yes,
What
Petal.
about the picocoulomb? That one, I say 1 times 10 to the power negative 12.
I've looked at a couple of question papers. That one rarely comes now, so it's not as much of focus. All right.
Okay. Okay.
Yes. So the ones that you would use most of the time is the nanomicro and the nanocoulombs. Then for the distance, I shouldn't preach this one because you guys should know this from like grade 7, but because it's you guys, I here 1 centimeter. 1 centimeter is going to be 1 by 10 to the negative 2 meters, because remember this has to be in meters. And then 1 millimeter, these are the ones you would commonly use, is going to be 1 by 10 to the negative 3 meters. Okay. So once we have that in mind, we are now able to then convert those units. Then we can start working on a couple of questions, just working on the Coulomb's law. So let's suppose you have a 10 um, nanocoulomb point charge. A 10 microcoulomb charge is centimeters 25 centimeters away from a negative 20 um, microcoulomb point charge. Calculate the magnitude of the electrostatic force between the two. You guys have 1 minute to do that, starting now. And you can raise your hand once you have the answer for that. How about you? You can't even let us finish writing the question. Yes, offense. What's the answer?
28.8 Newton.
Yeah, show off. Showing off. Anyways, it's F K Q1 Q2 over R squared. Then we perform the substitution. We know that Coulomb's constant is going to be 9 times 9. No, what's it is with me and the 9? Times 10 to the ninth. And then here you don't have to worry much about the substituting the charges. So you don't have to worry about the negative. Then Q1 and Q2 is those charges. But remember they are not in coulomb, so you have to convert them. So I'm gonna have the 10 first. The 10 goes in, so this will be 10 times 10. Remember this is now in micro. It is in nanocoulombs. No, it's actually in microcoulombs. So I'm going to convert its nanocoulombs, microcoulomb. That one times 10 to the negative 6 times 10 to the negative 6, and then the other one is negative 20, but I'm just gonna put in 20 times 10 also to the negative 6, and this is all divided by, and this is 25 centimeters away. Because it's centimeters, I have to convert this to meters, so this will be 25 times 10 to the negative 3, and thou shalt not forget the square. The Bible literally says that thou shalt not forget the square. Then if you put this into the calculator and it will do the work, you end up with 28.8 newtons. Any questions on that particular question? All right, no questions, I guess. Then let's take the second one, which is yes, there's a hand raised. Petro.
Why are you using the conversion of millimeter? Like, is it
The conversion of, I've used the conversion of
It's
millimeter. Oh, it's
yeah.
-2. Yes, it's -2. Times 10 to the negative 2. Yes, 10 to the negative 2, not 3. You're right. Okay, you still end up with 28.8 nonetheless. All right, so then the next one says the electric force. Take that as number 2. The electric uh, force between uh, charges, between 2-point charges, is 800 nanocoulombs. The electric force between 2-point charges with, not is, with 800 nanocoulombs and 900 nanocoulombs is 15 newtons. This time they gave us the charges and everything, and they want you to find how far apart are the charges. So how far apart are the charges? You guys have 1 minute starting now. You can raise your hand once you have the answer. Oh, yes, I forgot to mention. How far apart are the charges in centimeters? Yes, let's make things a little interesting. You may raise your hand once you have the final answer to that. Okay, and time. What is the answer? In centimeters. Before I start picking you all out of the crowd, and you guys are definitely gonna tell me I don't know or I don't have the answer. And Teresana is the first person I'm gonna choose. So Teresana has to pray that someone has the answer. What's the answer? Anyone? Anyone? Ah, Teresan. Terry. What's the answer?
So let me convert it first and then I'll get back to you.
Hmm. Hmm. I hear you. Memello.
Sir, I'm not yet done.
He. Tato.
Ish, I'm not yet done too.
Ah, guys. Okay. Hey. Anyways, back to Teresan. Since she said she's just converting, what is the answer for that in centimeters? Teresano. Yes, Terry. Final. How much did you get? Yes, Teresan.
You say, I wanna say, I'm not sure, but like
Mm.
I think it's 0.432 centimeters.
Oh, that
I'm
was
not sure.
painful. That was painful to hear.
But still,
Uh, Tato. Yes, Tato.
I got 2,08 centimeters.
Yes. Yes. It's 2,08 centimeters. Okay, so we start off with F is K, Q1, Q2, all over R squared. Then we perform the substitutions of what we have. So one thing we know is that the electrostatic force between those two is 15. So I'm going to have my 15, and this is just Newton, so I don't have to perform any conversions. Then for the K, I've got 9 times 10 to the ninth. And then for one of the charges, I'm going to go for the 800 nanocoulombs. So I'm going to have 800 times 10 to the negative 9, right? And then the other one, I'm going to have 900 times 10 to the negative 9. And then essentially, I'm going to find r squared. This whole thing becomes r squared, or rather, if I want to actually jump straight into r, I can say r would be the square root of the whole thing, which would actually be that stuff divided by the force. So if you actually look at the formula like this, you can do the direct conversion. You multiply both sides by r squared. You'd have r squared is equal to f r squared rather is equal to k q1 q2. There's a hand up. Yes.
It's the square root of 4,32 times 10 to the power negative 4.
No.
Yeah, square root of.
Oh, you mean the conversion? Oh, I thought you're saying that's the final answer. I was gonna be on your
No.
neck. So now let's just finish off the conversion. So here you're going to have r squared is going to be k q1 q2 over f, and then you square root the whole thing, and then it will take you straight to your answer. So here we'll just have the square root of um the k q1 q2. So that's just 9 times 10 to the ninth. Um, 800 times 10 to the negative 9, and 900 times 10 to the negative ninth, divided by the force, and the force being 15. The force being, yay, man. Oh, the force is here. This thing not moving. 15. And then you let the calculator do the work, and then you should end up with 2.08 um, centimeters. But if you, of course, when you do this whole thing in the calculator, you'll actually get the answer in meters, which is 0.0208 approximately in meters. Then you perform the conversion, and then you're going to get it in meters, which should be 2.08 centimeters. Any questions on that particular question? All right, I guess there are no questions. Okay, there's a hand up. Yes, Pedro.
Now in centimeter, I wrote 2 times 10 to the power negative 4.
You wrote what in centimeters?
No, yeah, in centimeters, I wrote in like 2 times 10 to the power negative 4.
2 times 10 to the power negative 4. Yeah,
Yeah.
but that should actually be the one in meters, not
Yeah, in
centimeters.
meters, in meters is 0,02 mus.
0.02. Yes. Then you're saying you
In
got
met-
2 times 10 to the power negative 4
in
for it
centimeters.
in
Yes,
centimeters.
yes.
Okay. But okay, it's fine, but I feel that you would have missed significant figures here. Reason being, if you convert this out of its scientific notation, you'd actually have something like 2,00. You'd miss the
Mm.
8. You see?
Yeah, yeah.
Yeah. So rather not have it in scientific notation for the sake of your significant figures. You do not want to miss those significant figures. Okay.
Okay.
Yeah. All right. Then let's take another one. You told a force of 500 newtons exists between identical charges, identical 2-point charges, okay, that are 40 centimeters apart. So this is the case. You are told that they are 40 centimeters apart. Now calculate the magnitude of each of the 2-point charges. So we want the magnitude of each charge. 1 minute counting now. You may raise your hand once you have the final answer to that one. Yes, Pedro.
I think it's 8,89 times 10 to the power negative 9.
8 comma
8. What?
8
Times 10 to the power negative 9. 8,
8 comma 8
8,89
8
times 8,89
8
times 10 to the
comma
comma
8 8 9
9.
8,89 times 10. Oh, that's horrible. Uh,
No, like just write 8,89 times 10 to the power
times 10 to the
times
power
10 to the negative 9.
negative 9. Anyone has a different answer? Anyone has a different answer? Ah, Tirisano. Hehe, I'm back. What answer did you get? Ivan, she ran away. Okay, Mamello, what answer did you get? Mamello?
So,
Hmm. What did you get for that one?
it's wrong. Very, very.
No, we don't know yet. None of us have the correct answer. But what answer did you get?
Hmm, I don't even want to say anything.
He. Hi. Okay. So let's work on the question then. So to start off with the formula, we can notice that the formula is going to tweak a little bit. So we still have Coulomb's law, KQ1, Q2 over R squared. But what we are told is the fact that they are identical. So I can actually change this to become KQ squared because they are the same. So I'm allowed to then combine them into one thing. Just totally multiply it as such. And then I have R squared. Even if you continue this way, you're still cool. Um, then we can perform the substitution. So I'm going to have the electrostatic force of 500 newtons. Coulomb's constant being 9 by 10 to the ninth. And I still have a q squared. And then the distance is 40 centimeters. So I have 40 times 10. If my maths is right, this should be negative 2 for that. So times 10 to the negative 2. Then we solve for q. So let's obviously not forget that this has to be squared. Many people forget that square. So I'm gonna do a quick solve. Uh, with a quick solve, you're gonna end up with q, not the q squared, being 9 comma 4 3 times 10 to the negative 5. Any queries on that? Yes.
Now on that equation, I use that one of E is equals to K Q1 over R squared.
E.
Mm-hmm.
Okay, I'm gonna explain the E part. Remember, E is not the same as F.
It's
When
like
we're talking about
strength.
E, it's actually
It's
the
this.
intensity of the electric field. It's not the electrostatic force between charges. So it's that would not be the best formula to use. Okay. So for those who are wondering what he's talking about, that is actually the next part we're going to then cover, which is the electric field intensity. Electric field, and that should be the last thing for the night. I'm exhausted as hell. Electric field intensity. So when we're talking about the intensity of an electric field, let's suppose we have a scenario where we can have, let's say, charge Q. What we know about Q is the fact that around Q there's a electric field. So there's going to be a field around it, like so, just some region around it. When an object gets into that region, it's going to experience an electrostatic force, either attraction or repulsion, either of those. And to calculate the intensity of that electric field, that's where we use the formula that says E is equal to K Q over R squared, where K is Coulomb's constant and Q is the charge. In this case, it is Q. And then we have the R squared there. Okay. So if we take this scenario of this Q and then around it, suppose I have maybe point X. Yes.
Isn't E the electric field strength?
It's the same thing as the intensity. I'd rather like
Okay.
referring it to it as intensity, just saying how intense or how like whoosh is it on that point on its electric field. That's the idea behind it. So I'm saying that when we have this X um at somewhere near the within that region of space that we're talking about, that electric field, we're going to have this force that is going to be taking place towards from Q towards that object. So with such questions, remember Q will have its own charge, but now X is taken as a point. We all we're going to take this point as positive all the time. Okay, and what we call this is this is what we call the positive test charge. We're always going to take that point that they want us to always refer to as positive all the time, and we're going to work on a couple of example questions where you're going to see this in action. So just remember that when they're talking about a certain point within that field, always take it as a positive. Okay, and this is us doing what they call that positive test charge. Yes, Petro.
But but sometimes they bring it as negative.
Remember, it is a point. They do not even necessarily have to give it a charge most of the time. So here, with we when we're working on questions where they want you to draw things like vector diagrams and so on and so forth, you would have to take that point as positive. That is the positive test charge that we're talking about. Let's actually take a question. So let's suppose we have charge Q1. So we're going to have charge Q1 and we're going to have charge Q2. So between Q1 and Q2, you are told that these are 1 meter apart. Okay, you're told that they are 1 meter apart. Then you have point P somewhere out here. There's point P, and you are told that point P is 12.5 meters away from this one. Actually, no, not 12.5. It's 2.5 meters. 2.5 meters from Q1. And then Q1 is 1 meter away from Q2. And then the charge of Q1, you're told that it is negative 2.5 micro microcoulombs. And then this one of Q2, you're told it is zero, not zero, 6 microcoulomb. Let's start off with just drawing the vector diagram of point Q, just to show how the effects of all these electric fields are on point Q. So I'm gonna start off with a dot representing that point Q. Then let's first analyze what is happening between Q1 and P. Okay, remember we're going to do a positive charge test. We're going to take P as if it is positive. And because P is positive and Q1 is negative, what is the electrostatic force between the two? Is that going to be an attraction or repulsion? Anyone? Attraction or repulsion?
Repeat again.
We're working on drawing the vector diagram. Right now, we're just analyzing between P and Q1. And we know that we're doing a positive charge test. P, we're going to take it as positive, and Q1 is given to be a negative charge. Do we have an attraction or a repulsion there? Yes, offense.
Attraction.
It's going to be an attraction. So because it is an attraction, then we can put in that arrow. So remember, we're working in terms of P. So we're actually going to have a force taking it towards Q1. That is the attraction that we are talking about. So this I'll then label as the electric field intensity of Q1. And then when we look at the one between Q2 and not Q2 and Q3, but rather Q2 and P. Remember, we're doing a positive charge test, so we're taking P as a positive, and Q2 is given to be positive. So do we have attraction or repulsion there? Yes, Pedro.
Repulsion.
You're going to have a repulsion. So because it's a repulsion, it will then be pushed there. But remember, the length of these lines will have to suffice to show this intensity. Remember, out of Coulomb's law, we have that formula, but you have to know how these things affect one another. So when you're talking about the electric field force, the electrostatic force, it is directly proportional to the product of the two charges, but it is inversely proportional to the distance, or rather the square of the distance. This is an inverse proportion. Okay, and because it's an inverse proportion, this guy is very far. This Q2, it's very far from P, and that's why we drew a small line there, because that intensity will be less. But then for Q1, it is more because it is actually close. That's why we gave the one for Q1 a longer line. So here, this is where we have the one of Q2. So always keep in mind the strength, the length of those lines. Okay, any questions on the vector diagram? Any questions? All right, no questions then. So now let's calculate the net electric field intensity. This is what we're going to start working towards. So remember, net just means we're adding everything. Essentially, we're just adding everything. But ultimately, we have to calculate each of them individually. So let's work on the Q1 first. So we want to find the electric field intensity of Q1 on P. So once again, the formula says K Q over R squared. Then I'm going to substitute Coulomb's constant, which is 9 by 10 to the ninth. And then the charge of Q1 is given to be negative 2,5. That. So here I do not, once again, have to worry much about the signs. You can, of course, put the sign, which will actually set you up for the net, but I'm going to omit the signs for now. So I've got 2,5 times, because this is in micro. Okay. So because it is then in micro, I'm going to say then times 10 to the negative 6 to convert it to coulombs. And then this is over the square of the distance. And the distance is already in meters, so that is just perfect. So I'm going to have 2,5, not 0. We're going to have 2,5. And this is squared. And then you let the calculator do the work. So 9 by 9 to the 9 by 10 to the ninth, and you've got 2.5 times 10 to the negative sixth over 2,5 squared, and that should ultimately leave you with about 3,600. Any questions on that? Any questions on Q1? All right, I guess we're fine with that. So then we can work on E of Q2. So the E of Q2, which is then this one, this is where we are now focusing on this towards P. So we still work with the very same formula. And then now we still do the electric field intensity, but then now the Q changes, which is now the charge of this one, which is the positive 6. Uh, West hand writing. The positive 6 times 10. Remember, we have to convert it to coulombs because this is in microcoulombs. So times 10 to the negative 6, negative 6 divided by, and this is 1 meter away. So 1 squared. And then you let the calculator once again do the work. Yes, there's a hand up.
No, it's
Yes,
not
Pedro.
one. It's 3,5.
It's
The
3,5.
difference.
Oh,
Yeah,
yes,
the
yes,
difference.
yes. Yes, we have to add the 1 meter plus the 2,5, which is, yes, 3,5. So that is 3,5. Yes. So we're going to have 9 by 10 to the ninth, and 6 times 10 to the negative sixth over 2.5 squared. And then you should be left with 8,640. Um, Once I forgot to mention this. This is in newtons per coulomb. Newtons per coulomb. You can put it as in n/c, or you can have it as n dot c to the negative 1. Either of those can work for your SI unit for that. Then that means now our E net is going to be. So looking at this, we're going to take the forward as positive. I like following the Cartesian plane, so we'll follow it as such. So this would be this minus that. So that's just 3,600 minus 8,640. And then we're going to get um 3,600 minus 8,640, and we're going to get a negative 5,040, which is therefore 5,040 newtons per coulomb. Any questions? Any questions on that? All right. Yes, Petro.
On that one, the second charge, I got 4,408,16.
For E2,
Mm.
this one. Okay. Let me double check it then. Okay, 9 by 10 to the ninth, and then we have 6 times 10 to the negative 6, and then this is divided by 3.5 squared. Uh, Not quite. Actually, that even makes me question the one that I have. It's not that. It's what 4,408,16. That's actually what I got now.
Yeah, that's what I got.
All right, yeah. So that should be 4,408, 16. Okay, so that changes the final answer as well, and that substitution ultimately. So we're going to have 4,408,16, and then this should leave us with a 3,600 minus that, which should be a negative 808, 16, which should be 808,16 newtons per coulomb. Okay, is that fine now? Okay, all right. Then let's take the final question. All right. So now you are given a situation like this. You have charge M and you have charge N. Okay, and you're told that the difference between the distance between charge M and N is 0.6 meters, and the charge of M is 4 nanocoulombs, and the charge of N is 6 nanocoulombs, and then at some point in between we have point X. and you are told point X is 0.2 meters away from N. Okay, and for that, they just want us to start off by drawing a vector diagram first. So that one is easy. So we start off with the dot. Then now we're looking at, let's start off here first. So and the one for in the intensity of N. Remember, once again, we're doing a positive charge test. We take X as positive as such. So we're taking X as positive, and this is given a positive as well. So that actually becomes a repulsion. So it does not go towards N, it actually goes away from N like that. And then when we're looking at M with regards to X, that is also a positive, and that actually goes there as well. Okay, and I'm making this one longer. Actually, that one should be shorter, not longer. Um, that one should actually be shorter because of the distance between M and point X. So it would actually have a less effect than this one, which is actually nearer. So this would be your E due to N, and this would be your E due to M. Any questions on the vector diagram? Okay, guessing there are no questions there. Then now the question here says calculate the net field at X due to M and N. So now they want the net field at X due to M and N. In other words, they're looking for E net. So you guys go ahead and calculate that one. You've got 5 minutes starting now. And once you have the answer, you may then raise your hand. Yes, Petro, what did you get for your answer?
Negative 1125.
Negative
Mm,
1125 newtons per coulomb.
no, no.
Anyone?
Yeah.
Okay. And who got a different answer? Anyone with a different answer? Okay. Let's work on it then, and let's see if that answer he has is correct. So let's work on the N first. Okay, there's a hand. Yes, Petro.
Yeah, it's two possible answers. Like it's negative and possible. Negative and positive. If you choose the left to be positive and choose the
Okay.
right to
Yeah.
be negative.
Yes. Okay. Okay. Let's calculate that regardless. Um. Let's work on the N first. So En, we still use the same formula of Q over R squared. Then the being Coulomb's constant is 9 by 9. What is it with me and the 9? 9 by 10 to the ninth. And then the Q being 6. So that is 6 times 10 to the negative 9 in this case because it is in nanocoulombs. And then this is over R squared, the distance. And this is just going to be 0.2 there's no need to convert that because it's already in meters, and I have the square there. Then we let the calculator do the work. Let me just type that in. 10. Okay, no, that's 0.2. 0.2 squared. Okay, I got 1350 for that. So 1350 newtons per coulomb. So that is what I get for N. Then for M, I'm gonna have to first simplify out that distance there. So that distance that we have there, I'm gonna have to take the 0.6 and minus out the 0.2 to have the distance between M and the charge X. So what I would have there is 0.4. Okay, so it being 0.4, then I can find out what is the electric field intensity of M, like so. So I still use the very same KQ over R squared. And then I have 9 times 10 to the ninth multiplied by charge Q. The charge is the one of M, which is 4 times 10 to the negative 9 over R squared. And the distance there is actually 0.4 after doing the whole subtraction. So I'm going to have a 0.4 squared. So I'm going to then let the calculator do the work. So 9 times 10 to the ninth multiplied by 4 times 10 to the negative 9 over 0.4 squared. And for that, I get 225 um, newtons per coulomb. Then suppose in my case, I'm going to take the right side as positive. I'm going to follow the Cartesian plane. I'm going to take the right side as positive. Then this will be the M minus the N. So E net would essentially then be E M minus E N. So which means I'm going to have 225 minus 1350. Okay, so 1350 minus 225 would give us 1125. Yes, 1125 newtons per coulomb. Any questions? Yes, Mamelo?
Sir, since like the electric field intensity is a vector quantity, are we supposed to specify the direction or anything like that?
It will always depend on the way in which they ask the question. There are times where they'll just ask you to calculate the magnitude only, and then if that's the case, you just give them the magnitude like we're doing so far. We're just calculating the magnitudes. But if they do ask you to give the direction, then you would stipulate the direction as such. All right. Any other questions? Any other questions? All right. Yes, Pedro.
Because I used the to the left as positive, and I got the answer is negative 1125, like
Okay.
nanocoulomb.
Okay. Yeah, that's in that case, since they said you should just calculate the magnitude, then you'd write it as a positive. Okay. But if there are those questions where they want you with a direction, you'd have to say therefore it will be 1125 newtons per coulomb, and then you'd stipulate the direction. So all you just have with that is you getting a direction. That's all you have. So as long as your magnitude is as such, you should be safe. Yes, Memelo.
Sorry, sir, I forgot to.
Okay. Any other questions? Any other questions?
We're fine.
You're fine. All right. So that was the last question for the for the day. So then obviously the next session would be for life sciences. Then if of course by decision we with decide to have another one, then we'll be continuing from electrostatics in two dimensions. This is for those scary questions that everyone hates, where you are given situations like you have a point there and a point there and a point there, and each of them are charges, and you have distances between them and those kind of cases. So those are the ones we'll be working on in our next sessions, and then we'll also attach it together with electric circuits. Okay, so
Okay,
I'll see
once.
you guys on is it Tuesday? Yes, on Tuesday for life sciences. All right. Good night, guys. You'll receive an email if you need to leave a review or any suggestions for the next ones. All right, guys. Good night. Yeah, but Kanti, are you still here or you have a question? Biggie? Hey, Biggie.